Okay, so here we are at the next lecture in the series on trigonometric functions. Here, this is the 5th of January 2017. And so, as you can see on the board, last time we looked at definition of angle in terms of degrees and radians. And in terms of radians, the angle can be written in equations like this in a simplified way. So these are equations for the arc length in terms of radius and angle. Angle must be measured in radians here and here. And we're also relating that to the arc length s, the linear speed v, excuse me, the angular speed omega, which is theta over t, and those linear and angular speeds are related by this equation, v is equal to r omega. So here we use these equations to find the linear speed of a satellite around the Earth, given its angular speed, which had to be calculated from this information. Okay, so now let me go on to the next section, which is in defining trigonometric functions. So today I want to introduce all the main trigonometric functions. There are going to be 6 of them, and also some relations between them. And hopefully, if we have time, a little bit of, I'll try to do some examples on the way. I'll do this for the special functions in particular, but please look through the examples yourself and do the try problems coming after each example in the textbook. And we're in section 7.2 now. All right, so let me begin here. Okay, so we have to start with, okay, so I'll discuss the trigonometric functions. Now we start with a right-angled triangle. So this is a triangle with where one angle is a right angle, namely 90-degree angle. So this is 90 degrees, or in radians, pi over 2. Okay, and oops. Given this triangle, I will call this side A, capital A. Sorry, this vertex is called capital A. This vertex is called capital B, and this will be capital C. Now it's a custom to label the opposite sides to those angles with the same letter but small. So this will be side little a, this is side little b, and this is side little c. So we must start with a triangle here. In order to do these definitions, we must start with a right angle triangle. So one of the angles is, and it's always going to be this one, C, is 90 degrees. And so I put that in the bottom right corner. Okay, so now the angle that I'm going to write here is going to be the Greek letter corresponding to B, which is beta, and the Greek letter corresponding to A will be alpha. So that's my labeling of this right angle triangle. Okay, so let me write some words in here. Now I suppose I start with a certain one of these vertices here, B, let's say, and the angle corresponding to it is beta. So I start with beta, and from the perspective of beta, I want to label these sides according to whether they touch beta or whether they don't touch beta. If it doesn't touch beta, then it's called the opposite side. So this side is called the opposite side. If it does touch, then it's either the longest side, which is called the hypotenuse, or simply the adjacent side. Okay, so now the definition of, now we can define the sine of beta, which I will abbreviate sin beta, is defined as the opposite over the hypotenuse. And the cosine, so I'll spell it out. Cosine again of beta. This means ditto, just the same as above here. Is cos beta is the adjacent over the hypotenuse. So those define these new, they're going to be real numbers. They're going to be ratios of the lengths of these sides, the opposite length over this adjacent length. And in this case, they will both be positive real numbers. So they may not be rational, they'll in general be irrational. Anyway, any real number. They could be any real number here. So you have to realize that also the triangle size does not matter here, because if you take two triangles with the same angle here and here, it will have the same angles everywhere. So if two angles are the same, then the triangle will be a similar triangle to the one before, and the opposite over adjacent, that ratio will stay the same. So it doesn't matter what the actual side lengths are in these definitions. The sine and the cosine of the angles will stay the same. There's also another standard quantity called the tangent of beta. I can write it out. And tan beta is the opposite over the adjacent. Okay. Now in terms of these numbers here, in the previous diagram, let's erase something here. The sine of beta is b over c. Cosine beta is a over c, and the tan beta is b over a. Okay, so see, I memorize these things. It's just a matter of looking at, for me, it's a matter of looking at where the angle is in relation to the sides. So as soon as I want to find the sine of beta, I look for the opposite side, which is b divided by the hypotenuse here, which is little c. And cosine of beta, likewise a, the adjacent over the hypotenuse c. Tan beta is the opposite. I look for that first over the adjacent, so b over a. I can also see if I can write these out in terms of the tangent. It can be expressed in terms of the sine and the cosine as the sine of beta over the cosine of beta. Because when you write that out, the b over c and the a over c will be in the expressions, and the c's will cancel out in the end. sorry, that should be B over C. And A over C. So the C's will cancel out and I'll just get B over A. All right, so this is already an identity that you can write down in terms of the trigonometric functions. So we can say that the trigonometric functions are not independent of each other. They have their identities. They have identities in terms of each other. Okay. Now, if we look at these, if we now look at the complementary angle, alpha, so alpha and beta are complementary angles. Complement here means when they complement each other, that means and one thing that can mean is two things complement each other if they go well together with each other in the English language. In this case, alpha and beta are angles which add up to 90 degrees. That's the mathematical definition of complementary. Or in our case, we can write that in terms of radian angles. Okay, so alpha plus beta is pi over 2 radian. Often we will consider our trigonometric functions in terms of angles which are measured in radians. Okay. So for the time being, though, I will give you the values of the I'll give you examples where I give you the values of these trigonometric functions for both the radian measure and the angle measure. So in terms of alpha, the results of finding these trigonometric functions are sine alpha. Here the opposite is A. So I look for the opposite, that's A. A over, and I have the same hypotenuse for beta is what you get for the hypotenuse of alpha. Sorry, alpha has the same hypotenuse as beta does. It's the same right angle triangle. So it's C that I divide by. And let's see, the cosine of the angle then is B over C, and the tangent of alpha is A over B. Okay, so already now I have some more relations. Here, this A over C is the same as cosine of beta. Okay, so the sine of an angle is equal to the cosine of its complement, which I can write as pi over 2 minus alpha. All right, so this whole thing here, especially when I write it in terms of with the same angle on both sides, so it's just, there's no beta now. Sine of alpha is equal to the cosine of pi over 2 minus alpha. That's called a cofunction identity. And similarly over here, cosine of alpha is the same as the sine of beta. Which is the sine of pi over 2 minus alpha. And the tangent of alpha is b over a, or a over b, which is 1 over b over a, or 1 over the tangent of beta. Here I have it as 1. I can also write it 1 over tan of pi over 2 minus alpha. Okay, so these are all called the cofunction identities, or some of them. I'll write a big box around all of them. Okay. Now, in the following, yes, okay, before I give some examples, I'll just give you the rest of the definitions of all of the trigonometric functions. Okay, so this particular identity, where I express tan alpha in terms of 1 over tan beta, suggests that I define a new trigonometric function, namely the cotangent. So the cotangent of this angle beta, or of any angle beta, is equal to 1 over, cotangent. So it's written like this, but it's spelled cotangent. So COT beta is simply 1 over the tan of beta, tangent of beta. So that's the cotangent function. And the other functions are similarly invented in order to describe the reciprocals of the sine and the cosine. So we have the secant of beta is sec, SEC, is 1 over the cosine of beta. And finally, the cosecant of beta is spelled CSC beta, is simply 1 over the sine of beta. So these are the further definitions. Of the rest of the trigonometric functions. All right, so now these three are kind of are easy once you have the first three. The last three are just the reciprocals of the first three. So notice that. So that will help you solve the problems quicker. If you're asked to find, if you're given an angle, beta, and you're asked to find the values of these trigonometric functions, then you have to construct, say, some triangle to find the side lengths, and then you take the reciprocals. Then you take these ratios here to get sine, cosine, tangent of that angle, and then you can find the reciprocals right away and get all the rest of the trigonometric functions. So you get 2 for the price of 1, so to speak. If you can solve for these 3, then you get the other 3. All right. Now I want to give some particular examples, special case examples. So we have special angles here. Okay, let's do the 45 degree, and 90 degree triangle case. So in this case we have a triangle whose 2 small side lengths are the same. All right, so this is called an isosceles triangle. So this side is length A, this side is length A. And what's the third side length going to be? Well, let's remember that the Pythagorean theorem holds for a right angle triangle. So we have here A, B, and C. Pythagoras theorem says that the sum of the squares of the two small sides equals the square of the large side. So a squared plus b squared is equal to c squared. That's Pythagoras' theorem, or the Pythagorean theorem. Okay, so if we have that, so this is true in general. So if A is the same as B, what then is C? Well, you could just substitute that in and you get a squared plus a squared. So this is in our example. A squared plus a squared is equal to c squared. So I just add that, and that's 2a squared is equal to c squared. Then I take the square root of both sides and I get square root of 2a is equal to c. So that notice the a is it's not underneath the square root sign, it's outside of the square root. The square root only applies to the 2. So root 2 times a is equal to c. So we could replace this with root 2a. Now, or we can even simplify this. We can say a is 1, since it's a similar triangle, doesn't change our angles. And these sides will be, these angles here will be 45 degrees each. Why is that? It's because the sum of all the angles of any triangle must be 180 degrees. That means alpha plus beta plus pi over 2, or 180 degrees is also pi radius. Okay, so that shows you why this is pi over 2 here. So the sum of alpha, beta, and pi over 2, let's write it right here. That's pi over 2. Is pi. So alpha plus beta is pi over 2. Okay, so that's why the two other angles besides the right angle in a right angle triangle are always complementary. They always add up to 180. Okay, in this case, alpha and beta are the same, so 2 alpha is equal to pi over 2, or alpha is pi over 4 radians, which is the same as 45 degrees. Okay, so here's my triangle then. 1, 1, square root of 2. This is pi over 4. This is pi over 4. And that's, of course, 90 degrees, symbolized by the square sign there. The little square. So what's the sine of this angle? The sine of pi over 4 then is 1 over square root of 2. Which can be written in a more standard way as 1/2 times the square root of 2. So I've taken the roots out of the denominator and put them only in the numerator. Then I have the cosine of pi over 4. Because of the symmetry of this triangle, that's going to be the same, because it's the adjacent, which is 1. Yeah, this would be the opposite, which is this 1 over root 2, if you're looking at this angle. And this will be, again, if you're looking at this angle, the adjacent, which is this side 1 over the square root of 2. But it's the same if you look at it from the perspective of this angle because of the symmetry. So it's, again, the same. 1/2 times the square root of 2. And the tangent of pi over 4 is likewise 1 over 1, which is 1. Okay, so those are the special values for the trigonometric functions for 45 degrees or pi over 4. The other values for the other trigonometric functions are, again, can be computed by taking reciprocals. This is 1 over 1, which is 1. The secant of pi over 4 is the reciprocal of the cosine, which is root 2. And the cosecant of pi over 4 is, again, root 2. So these are the special values, or the values for the special angles. Let me say that again. These are the values of the trigonometric functions when evaluated at this special angle pi over 4. Okay. Let's look at the next case, which is 30 degree, 60 degree, 90 degree triangle. Okay, so now this is not going to be an isosceles triangle anymore. Pythagorean theorem will always be true here still. So we'll use it. So what I'll draw here is, okay, so here's my, let me draw this better. Okay, so what I'm doing here is I'm drawing a 60, 60, 60 triangle first, and then I'm cutting it in two here by drawing the perpendicular bisector from this vertex, and that will intersect at right angles. So the perpendicular bisector will, of this angle here, will be, the bisector of this angle will hit the base at right angles. So this will be 90 degrees. And this was a 60-60 triangle. So this started with 60 degree triangle. So this we knew was 60 degrees. This is divided by 2, so now this is 30 degrees. And this, by the way, is also 30 degrees, and this is 60 degrees. And here we've introduced a new vertex, and that's going to be also 90 degrees. It's going to go back to 90 degrees. Okay. 90 degrees. All right, I'm just checking my voice here to make sure the signal's coming through good. All right, and now let's pick a particular side for this starting triangle. So we'll pick 2 for the side length of the 60-60-60 triangle. Okay, so this starting triangle is called an equilateral triangle because all the sides are the same and all the angles are the same. Equilateral triangle. But when I divide by 2, it's neither equilateral nor isosceles. It's called a scalene triangle. All right. Maybe that's not quite true. It's a right angle triangle. Scalene, I think, is all 3 sides are acute. All 3 lengths are acute and not unequal to each other. And the angles are unequal, so the sides are also unequal to each other. Anyway, this equilateral triangle is divided into 2, and I get a right angle triangle which is 30, 60, 90. So this is what I'm looking for. So this side length will be 2. Now because I've divided this side into 2, this side length will here be 1. So let's draw it again. Okay, now my 30, 60, 90 degree triangle looks like this. And let me write it in radians. Sorry, I want to write this so you get used to radians more. Okay, so pi over 6 is the angle in radians. That's for 30 degrees. Pi over 3 is the angle in radians for 60 degrees. And I'll continue to leave this as a small square to indicate pi over 2 radians, which is 90 degrees. So this side length is 1. This side length is 2. What's the third side length? Well, there we can use Pythagoras' theorem again. So this side length is A, this side length is B, and the hypotenuse is 2, which I call C. So again, A squared plus B squared is equal to C squared. By Pythagoras. And so we can solve for A squared by plugging in B squared, which is 1. 1 squared is 1. And then C squared is 2 squared, which is 4. So A squared is 4 minus 1 is 3. And I take the square root of both sides, and I take the positive square root, so because B is, or A is assumed to be positive. So that's my side length in the end, the square root of 3. Okay, so here's my picture then. For pi over 6, pi over 3. Okay, so let's start with pi over 6. The sine of pi over 6 then is the adjacent over the hypotenuse, which is, I'm going to erase all of these here, because they're all different. Sine of pi over 6 is going to be square root of 3 over 2. All right? I'm starting with sine of pi over 6 here. What's the cosine of pi over 6 radian? It's the opposite over the, I'm sorry, I wrote it, sorry. Yeah, it's the opposite over the hypotenuse, so it's 1 over 2. Cosine of pi over 6 is the adjacent over the hypotenuse, which is root 3 over 2. And the tangent is the opposite over the adjacent, which is 1 over square root of 3. And here I can rewrite this as 1 over 3 square root of 3 to rationalize the denominator. Then the cosine of, or the cotangent of pi over 6 is 1 over that, so that's the square root of 3. 1 over just the previous one. The secant of pi over 6 is 1 over the cosine of pi over 6, so that's 2 over the square root of 3, which is 2/3 root 3. And the cosine of pi over 6 is 1 over 1/2, which is simply 2. Okay, so once you get the hang of this, these are not too hard to actually memorize, or you can easily draw the diagram with the numbers and write these down. You know, it's easy to remember numerically. This turns out to be 0.5 numerically if you write it in decimals, and this turns out to be 0.866. So this will be a little bit bigger in value than this number here. Okay, and in fact, it will turn out to be the case that whenever the angle is less than 45 degrees, the sine of the angle will always be less than the cosine of the angle. You can see that from the shape of the triangle. When this side is less than 45, this side will be less in length than this side. And the tangent for that case will always be less than 1. The cotangent will be always greater than 1. By the way, these are always going to be less in 1 than in absolute value. You can see that by the decimals. And these two will always be greater than 1 in absolute value. Now, before I do too much here, there are some other special cases which are kind of limiting cases of the triangles. You can define the sine of 0 degrees. 0 degrees will be this triangle in the limiting case of taking the opposite side to be shorter and shorter. So b goes to 0. Then in that case, a is equal to c. A is equal to c. So the opposite over hypotenuse is, and they're not, let's say it's equal to 1 for simplicity. In fact, you could take it to be any real number, and it'll still work. So you basically, you take the hypotenuse, and you flatten it out against the adjacent side. So then you get b over c, which is 0. The cosine of 0 degrees is a over c, which is 1. Because a divided by, they're the same. And the tangent of 0 degrees is 0 over 1, which is 0. Now notice also that, and this is also true for radians. So if 0 degrees is the same as 0 radians, so I can just write 0 here, and that means the radian measure, which the value is the same, 0 for each one, for each measure. Okay, so the cosine of 0 degrees is undefined, because I'm taking 1 divided by 0. And the cosecant, or the secant of it, is 1 over 1, which is 1. And the cosecant is again undefined, because I'm taking 1 over 0. Okay, so you can't divide any positive real number by 0. It's an undefined operation. All right, and similarly, if you take pi over 2 for the angle, so you now take the opposite side and you flatten it against the hypotenuse. Then the sine of the angle will then go to beta will go to pi over 2. So the sine of pi over 2, or 90 degrees, is 1, and the opposite and the hypotenuse will be the same. Let's write this in terms of c and b. So here a goes to 0, and b and c are the same. So the sine of pi over 2 is 1. The cosine of pi over 2 is 0. The adjacent is going to go to 0. And the tangent of pi over 2 is going to be 1 over 0, which is again undefined. The cotangent of pi over 2 is 0 because it's the cosine over the sine. And finally, the secant of pi over 2 is undefined. And the cosecant of pi over 2 is 1. So we see, again, these two functions are both less than 1 in absolute value, or equal to 1 possibly. In this case, one is equal to 1, the other is 0. And the others are always greater than or equal to 1 in absolute value. In this case, this goes, you can think of this as undefined or going to infinity. As you approach this angle, this function, these functions will go to infinity. Both in this case for the angle going to 0, and for this case for the angle going to pi over 2. Different functions will go to infinity here than they do here, of course. Here it's the cotangent and the cosecant functions which go to infinity. Here it's the tangent and the secant functions which go up to infinity. Okay, so that covers our special angles. Now you can write a table as an exercise and know how to complete this table. It will help you to remember all these angles if you practice this. So you so what you do is you write the angle on the top here, so 0, and then all the special angles, so pi over 6 in their order, pi over 4, pi over 3, what's the next one? So you go around the circle, and you look at all these special angles. So you get this divided into 3 and also divided into 2. Okay, well first the main angles will be, we'll start with these: pi over 6, pi over 4, pi over 3, and then pi over 2. We'll see later that the sine, cosine, tangent, and so on, all those trigonometric functions, all 6 of them can be defined for angles which are greater than pi over 2, okay, when you go into this region of the circle. When the base of the angle is on the x-axis as usual, and the terminal side is in the second quadrant. So for now we're just looking at the first quadrant. Okay, so what you do is you write, the diagram, sorry, is in the way here, so I'll just erase it. This is a little bit, shouldn't be there. Okay, so the sine, so this is my angle alpha, let's say, and the sine of alpha, cosine of alpha, tangent of alpha. And then we have, well, I'll just take the reciprocals of each in order. So cosecant alpha, secant alpha, and then cotangent of alpha. So draw the lines, and then you can just fill in the table. So practice this. Okay, you can write a sheet and then just send it to me. Okay, you can practice this and just send me something for an assignment here. On one piece of paper. So okay, maybe we wait on that, and I'll have you do that for all of the angles up all the way around. Actually, it's going to be, you have to draw more, 4 times as much, I guess. So so far we have 0 for the angle 0. You can just write in these special values right away. The cotangent is, we'll just write undefined infinity, I guess, for if it's 1 over 0. Cosecant is infinity again. Secant is, so these two are 1 and 1. And up here, I take, in fact, it'll just be the reciprocals of these values because pi over 2 is the complement of 0. So the sine is the same as the sine of the angle is the same. Sorry, this should be 1, and this should be 0. Then the tangent is the reciprocal, which is infinity. This is the reciprocal, which is 0. This is 1. Sorry, this is infinity and 1. So you just interchange these to get the. It's just what we have down here anyway. Okay. And then you can fill in the values. So these are interchanged because the sine of an angle is equal to the cosine of its complement, and these are exchanged because when you take the reciprocals of that identity, namely the sine of an angle is the reciprocal, or the same as the cosine of the complement, you take the reciprocal of both of those sine and the cosine of the complement, and you'll also get an equality. They must be the same. So this gives you that the cosecant of alpha is the secant of the complement. All right, so we could just get the values by interchanging sine and cosine here, and the secant and cosecant. Sorry, this should be 1. This should be 0. Sorry, that's the cotangent right there. Okay, and the tangent going from here to here, these will interchange because because also the tangent of alpha is equal to the cotangent of the complement. Right, so we're just writing the original ones, these all together. These are called the cofunction identities. Okay, so how about the rest of the values here? So this was, we saw 1/2. This is 1 over square root of 2. I'll make it simple by not rationalizing the denominator. And this is root 3 over 2. And this is root 3 cosine of pi over 6. Yeah, root 3 over 2. Same thing, 1 over square root of 2, and this is 1/2. The tangent is 1 over the square root of 3. Tangent here, it's just the ratio of this over this. This is 1, and the ratio of this over this is the square root of 3. The cosecant of alpha is the reciprocal of this, the sine of alpha, so that's 2. This is the square root of 2, and this is 2 over root 3. And then the secant of alpha is 1 over this, so that's 2 over the square root of 3. Square root of 2 again here, and 2. And the cotangent of alpha is just the reciprocal of these values here. So this is root 3, 1, and this is 1 over root 3. Okay, so know how to get these values easily or quickly, or memorize it somehow. The best way, I think, is to just draw the little picture, and then you can read off just by memorizing definitions, of course, main definitions, and putting together the ratios. All right. And it's pretty simple because they're all 1s, 2s, and 3s, and square roots in there. All right? If you draw it in that simple way. Okay. Now, I want to discuss the unit circle approach to the trigonometric functions. So the unit circle allows us to extend the definitions of the trigonometric functions outside of this quadrant. So far we'll have, it's good that we can define the trig functions for all these angles, but they're always between, the angles that you have to put in here are always between 0 and pi over 2. And by the way, these are the easiest angles to figure out, but in general, it's not easy to calculate the angle. We'll have angles different than these values here, between 0 and pi over 2. You'll need a calculator to calculate them. I mean, there are some special angles like pi over 8, which can be written as in terms of square roots, but usually they're always going to be, very rarely will you get a rational number. You'll get more likely an irrational number, even for special angles. Further special angles you'll get by dividing some of these by 2, like pi over 12 or pi over 4, right? And using so-called double angle formulas, which we'll see later. Okay, so the unit circle approach allows you to extend this to all the 4 quadrants. Okay, so here are our 4 quadrants. Here's the x-axis, here's the y-axis. Remember how quadrant 1 is where all the values of x and y are positive. All the coordinates x and y have positive values. Both coordinates have positive values. Quadrant 2, so you just go counterclockwise to get to all these quadrants, just in the same way as you would go if you were increasing the angle from 0. quadrant 3 is here, and quadrant 4 is here. So it's all in that order. So in quadrant 2, so here x is positive and y is positive. Here in quadrant 2, x is negative and y is positive. In quadrant 3, both coordinates are negative. And in quadrant 4, x is positive and y is negative. Okay. So in the unit circle approach, let me draw it again. We'll draw the unit circle. So the unit circle has a radius of 1. And the center is at 0, 0. Center is at the origin of the xy axis, of the xy plane. Okay, so this point will be 1, 0. This point will be 0, 1. This point will be minus 1, 0. And this point will be 0, minus 1. Okay, so the way to get the value of a trigonometric function for a certain angle is you draw the angle. So now let's say the angle is over here. Let's measure it again from the positive x-axis all the way to another ray. Okay, so let's call the angle alpha. No, let's call it t. So t will be now, I know it's not a Greek letter now, t will be a real number. T is always measured in radians. So we'll see that if you measure the angle in a Roman number, this is called Roman, not Greek, then it will almost always be measured in radians. It's just a convention. Whereas if you show the angle as a Greek letter, then you could label it either way, as radians or degrees. Okay. So now we'll call this angle t. Okay, so the simple definition that we'll have now is that the sine of t. So you draw the extra ray, and now you look at the coordinates of that point. So they'll be x and y. So the sine of t will be simply y. So it's the y coordinate of this point. Cosine of t will be x, and the tangent of t will be y over x. Why is that? Well, when we do this in the first quadrant, it's easy to see why. So here's the unit circle. In the first quadrant, here's our point xy. If we drop the perpendicular from that and get a right angle triangle, the unit circle has radius 1. That means this length here of the ray from the origin to where it intersects the circle, that length is 1. And so the hypotenuse will be 1. And the angle here will be t. The adjacent side will be just the value of x, because that's how far I have to go along the x-axis to get to that point, before I go up, of course. So I go along the x-axis by a distance of x, and then I go up towards the point parallel to the y-axis by the distance of y. I can do that in the other order, of course, as well. Right, go up y first and then across by x. In any case, the triangle that I get will have these measurements. X will be the adjacent, y will be the opposite, and so that means that the sine of the angle t will be the opposite, so y over 1, which is y. And the cosine of t will be the adjacent over 1, which is x over 1, which is x. And the tangent will be the opposite over adjacent, which is y over x. So the tangent of t is y over x. We also have the other trigonometric functions. Cosecant of t is 1 over y. Right? If y is not 0. Otherwise, that will go to infinity. The secant of t is 1 over x, and the cotangent of t is x over y. Okay, so in terms of the unit circle, so notice that these values of x and y are not independent anymore. They always have to lie on the unit circle. So that means the equation for the unit circle must apply, which is x squared plus y squared is 1. The distance from the origin to any point in the circle is always 1. So that's where that equation comes from, if you'll recall. All right, so let's also, and what does that mean for the sine and cosine, by the way? Well, if we plug in the sine and cosine, those are y and x respectively. So if we plug in y and x into this equation, we get, I'll just interchange the order a little bit. So it's sine squared t plus cosine squared t is equal to 1. Notice how I'm writing this squared. I don't have to use brackets when I do this. I'm writing the square right after the sine itself, so that indicates it's the square. You first take the sine of t, and then you square that number, whatever it is. And so these will be, it's another way of writing this without using the cumbersome brackets. Okay, so this identity is another trig identity, trigonometric identity, which we'll see a lot, which is always true, okay? So you'll notice when I go outside this quadrant, these definitions will still hold. All 6 of these definitions will still hold. And in the other quadrants, some of the values of x or y or both will become negative. So some of the values of these trig functions will become negative. But when I square a negative number, I'll always get positive. So, and I'll still be, the coordinates of x and y will still be on the circle. So this will always be true. All right, so now let's see. What happens to when I find the trigonometric functions of some of these larger angles? Okay, so now my table, I'll just look at the dividing the triangle into 8 pieces, the angles that come from that. So this is going to be pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and then 0 or 2 pi. So the table tells me, or if I have to write these angles in now, on the top. So 0, pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and then 2 pi. And And here I'll write the sine of alpha. So these are all alpha values. Sine of alpha, cosine of alpha, tangent of alpha. Let's just do those three. So I won't do the complete table, but I'll ask you to do that for me, please, for an assignment. As well as to do this for all the other angles in between for that are coming from the 1/12th circle, dividing the circle into 12. So you'll get pi over 6, pi over 3, and so on. So I'll just do some sample values. So the sine of 0 is 0, cosine of 0 is 1, tangent of 0 is 0. And then I go to pi over 4. This is 1 over root 2, 1 over root 2, and 1. And this is going to be 1, 0, and undefined or infinity. Okay, so that was from the previous table. Now let's see, 3 pi over 4. Here, this angle is similar to the pi over 4. It's just a reflection in the y-axis of the pi over 4 line. So if we reflect in the y-axis, that line, what does that do to the coordinates of this point? Well, this is xy. So if we reflect in the y-axis, that changes what? The coordinate of only x. So we get minus xy over here. So it just changes the sign of the x coordinate. But that's going to be this thing here, cosine of x, cosine of the t, I should say. T is what should be written here. Is that is the only thing which changes sign. So I look over here, it's 1. I look over here, it's 1 over root 2. So that's going to be minus 1 over root 2. And the sign is the y value. That does not change at all. So that's 1 over root 2. And finally, the tangent is a ratio, and that's going to be minus 1. For pi, that's also a reflection in the y-axis of this line. So again, cosine changes to minus 1. This does not change, and this is the ratio of the two. Again, it's 0. Now in this quadrant here, I get both are negative coordinates. So it's a reflection of both the x in the y-axis and the x-axis. So in that case, after reflecting in both x and y-axis, this point goes from xy to minus xy to minus x minus y. So both coordinates are negative then, so I get minus 1 over root 2, minus 1 over root 2, and the ratio is the minuses cancel and I get plus 1. And finally, I'm going down in this direction, 3 pi over 2. There, that's going to be a case of reflection about these values, about the x-axis. So that will just change. Here, this reflection only changes the sign of the y-coordinate and leaves the x-coordinate unchanged. That's true in general. So only the y-coordinate changes sign, the x-coordinate stays the same. So this is the y-coordinate, that changes sign from this value, which is 1, so that goes to minus 1. And this value stays the same, so that's 0. And then the ratio is, again, I'll call it infinity, is minus 1 over 0. You might say, well, that should be minus infinity, and that's yeah, you have a good case there, but usually when we think of infinity, it's plus or minus infinity. It's a completely big number, a completely large negative number. And often you'll have asymptotes where on one side you go and it goes to plus infinity, the other side you go and it goes to minus infinity. So the two are actually pretty closely related. All right, so for this one, 7 pi over 4, you get, it's the reflection of this guy in the x-axis, and so only the y will change sign. So you look at the pi over 4 value, that's a y, so that changes sign. This stays the same, and this is a ratio of -1. And finally, 2 pi will be the same as these three values. Okay, so just looking roughly here, the sign of the angle is positive in the first quadrant, and then in the second quadrant it stays positive because it's the y value of the point of the unit circle, of the coordinates of the point of the unit circle. And then after the angle pi, it changes to negative, and it stays negative with a maximum negative value here of -1. Or it's actually minimum of the -1, and back up to 0 over here. And if you put the values of the other angles in, it will continue that pattern. Now in this case, the cosine of the angle is the x-coordinate. It stays positive only in the first quadrant, then in the second it changes sign and stays negative throughout the second and third quadrants. And in the fourth quadrant, only in the fourth quadrant does it become positive again. And finally, the tangent alternates. It stays positive in the first quadrant, then becomes negative in the second quadrant, becomes positive again in the third quadrant, and then is negative in the fourth quadrant. And again, all the other angles that you'll calculate will bear that out, will be consistent with that, have the same properties. All right, so now let's try this for some other angles. We've been considering special angles here, where the sides might have rational side lengths or irrational side lengths. Let's consider other cases where you have rational side lengths which are well known. So this is the so-called three, 4, 5 triangle. Sorry. Okay. So here we're not geometrically constructing any angles. We're just geometrically constructing the sides first as these whole numbers. And this is known to be a right angle because of Pythagoras' theorem. Pythagoras' theorem is true in the other way, in that if you take the sum of the squares of the two small sides and that equals the square of the large side, the hypotenuse, then the angle must be 90 degrees. And indeed this is the case, because you get 9 here, 16, and that equals 25 when you add them. All right, so for this case, you need a calculator to calculate the angle. The angle will be such that the sine of the angle alpha is equal to 3 over 5, or in other words, 0.6. Or you can calculate it by the sine of alpha is 4 over 5, which is 0.8. Now notice if you take the sum of the squares of these, it should equal 1 if everything is okay as I set it, if everything follows this identity, which I said was always true. So is it equal to 1? Well, 0.6 squared is 0.36. 0.8 squared is 0.64. And yes, if you add those, that's 64 plus 36 is 100, but there are 2 decimal places, so that is indeed 1. Okay, but what is this angle? How do you get that? Okay, so I'm saying we need a calculator, so I'll just get up my trusty Canon F71 5SG here, and I plug in. So I'll need to use what's called the inverse functions here. So in the same way that we have logarithms, are inverses of the exponentials, that helps us to solve exponential equations like e to the x is equal to y. In other words, the solution there is x is equal to ln of y. Here we also have inverse functions which allow us to solve this equation, and those functions are on the calculator. So here if I solve, I just take the inverse sign of both sides. The inverse sign of the sine is equal to alpha itself. So this is sine inverse of 0.6. So that's how I have to get it on the calculator. So I take the inverse sine, shift sine inverse of 0.6, and I get an angle in degrees. The angle in degrees is 36.87 degrees. 36.87 degrees. To get the results in radians, let's see how to do that. Either you get the results in degrees and then use your conversion factor, which is pi over 180, or you can set the calculator in radian mode. And I'll have to figure out how to do that. Oh, here it is. So I have to go to the bottom there, and it's DRG is the button I have to press, so it's Shift DRG. Then I choose the second one, which is radians. The R means radians. Oops, and then that gives me an error, so what's going on? Okay, let's try that again. Shift. Oh, I have to take the angle and then... Yeah, okay, so one way is you calculate the angle first, and then you do this... You change the angle. Okay, I haven't figured that out, so I'm not going to spend your time by figuring it out here. I'll do that later. Okay, but you can get the angle in radians, and it's going to be something, again, it's going to be a rational. It's not a simple multiple of pi. It's not a rational multiple of pi anymore. Okay, so let's just, yeah, let me just try it again for at least this case. So inverse sine of 0.6, so that's giving me something in degrees, 36. It's about 36 degrees, and that jives with, the diagram here. Less than 45, bigger than 30. And if I change it to radians, let's see. Yeah, it's 2.1. Oh. Okay, yeah, let's see. I'll do this again here. Inverse sine, shift inverse 0.6, so I get that, and then I tried answer degrees. Okay, it's giving me degrees. How come I can't get radians here? It's giving me 2,000 something, so I doubt that's right. It should be a smaller number. It should be closer to. Let's try this again. 1. Something's funny here. Okay, sine inverse of 0.6. So I multiply by pi and divide by 180. Okay, so I should get, this is what I should get, 0.6435. And then there'll be zeros, you can round it off to this. So 0.6435 radians. All right. What are the other? So for that angle, 36.9 degrees or 36.87 degrees, what are the trigonometric functions of that angle? So we have already the two that we've written down here, 3/5 and 4/5, or 0.6 and 0.8, and the tangent of that will then be sine over cosine, which is 3/4, that's 0.75. And the cosecant will be 1 over this one, so that's going to be 5/3. The secant of alpha will be 5/4. And you can write these as decimals to some number of decimal places is 1.6667 or something. Round it off. This is exactly 1.25. And then the cotangent of alpha will be 4/3, which is 1.333, etc. So round it off to 3 decimal places, you get that. All right, so anyway, now you learn your calculator. That's why please look at your instruction manual for the calculator. And it's beyond 1:15 here, so I'm just going to stop this video here. And we'll continue on next time with trig functions, okay? Have a good day, Kudofis. And by the way, Nowruz Mubarak. Forgot to say that before. So sorry about that, and have a good day. Take care and bye.